Welcome to today's Explainer. We are diving headfirst into a literal scientific cold case today. We're going to unpack physicist Lee Smolin's brilliant and honestly highly controversial critique on exactly why theoretical physics has been stuck in a multi-decade rut. Seriously, if you've ever wondered why we don't have warp drives, teleportation, or, just an entirely new understanding of energy yet, well, you are definitely in the right place. So I want you to ask yourself, when was the last time we fundamentally changed how we view the universe? And I mean a real, paradigm-shifting breakthrough about the laws of nature that we could actually tangibly prove. Because sure, we've got way better smartphones, ridiculously fast computers, and these incredible space telescopes, but a totally new law of reality? It's been a surprisingly long time. Just think about it. Compare the explosive early 20th century, that true golden age with Einstein and Maxwell just teeming with proven discoveries, to the stark reality of our modern era. For decades now, foundational, proven progress has virtually ground to a halt. We've kind of hit a massive wall. Here's how we're going to crack this case today. We'll look at the stagnation crisis, the 5 great mysteries, the string theory promise, the landscape of failure, academic groupthink, and finally, saving physics' future. All right, part 1, the stagnation crisis and a century stalled. Let's look at the cold case itself and figure out why science is so completely stuck. So Lee Smolin points out this massive paradox, and it makes a lot of people in academia super uncomfortable. Think about it. Despite having unparalleled funding, immense technological resources, and literally some of the greatest brainpower in human history, we are missing one absolutely crucial thing: observational proof. We have this incredibly complex math, but zero experimental confirmation to actually back it up. Moving on to part 2. The 5 great mysteries unsolved. These are the massive, looming walls standing right in our way. These 5 fundamental problems are essentially our primary suspects. Physicists have been desperately trying to crack them for over half a century. We're talking about merging relativity with quantum mechanics, resolving the very foundations of the quantum world, unifying particles and forces, explaining those bizarre constants in the Standard Model, and of course, figuring out what the heck dark matter and dark energy actually are. Now, the most notorious of all these unsolved mysteries, that's quantum gravity. This is the holy grail, you guys. It's the missing link that researchers hope will finally marry the physics of the very large with the physics of the very small. Because right now, we basically have 2 totally different rule books for the universe, and that simply doesn't make any sense. And here is our core conflict. On one side, we have general relativity. It beautifully governs gravity, stars, the whole cosmos. On the other side, quantum mechanics, which governs the microscopic world of subatomic particles with just unbelievable accuracy. Both work perfectly in their own domains, but mathematically, no way. They absolutely refuse to work together. They just break down into infinities. Which brings us to part 3, the string theory promise. Enter the shiny mathematical framework that promised to be our lead detective. String theory came onto the scene with incredible hype. By reimagining our universe's fundamental particles not as tiny little dots, but as microscopic, vibrating strings, this theory initially looked like the elegant theory of everything we desperately needed. It seemed like the perfect mathematical bridge to finally unite gravity with the weird quantum world. But here is where things get really strange, the number 11. To make the incredibly complex math of string theory actually work without totally breaking its evolution, which is known as M-theory, requires our universe to operate in 10 or 11 dimensions. But we only experience 3 of space and 1 of time. Right out of the gate, we're dealing with invisible, curled-up dimensions that we literally cannot see, touch, or test. And that leads us to part 4, the landscape of failure. This is the shocking twist in our explainer, where our star detective suddenly becomes a massive false lead. Just look at this comparison. Despite massive early promises to provide a single, beautifully unified theory, string theory mathematically devolved into a landscape of virtually infinite possible solutions. I mean, it could describe an infinite number of different universes, but it couldn't specifically predict ours. And the absolute worst part? 0 observable, testable predictions. Literally nothing we can verify in a lab or with a telescope. So the crucial point here, and this is a real game changer, is that because this mathematical landscape is so incredibly vast, it can accommodate almost any universe imaginable, which means it can never actually be proven wrong. And in science, if an idea cannot be tested and potentially proven false, it loses all its power. It becomes scientifically hollow. It's more like a philosophy than actual physics.
All right, part 5, academic groupthink and systemic flaws. This begs a really important question.
If the theory is essentially untestable, why does almost everyone in academia still study it? Why do we continue to pour billions of dollars, endless grants, and our absolute brightest young minds into a theoretical framework that just hasn't yielded real-world answers?
Well, Smolin argues the answer isn't in the math at all, it's actually in human behavior. He points straight at the sociology of science, revealing a deep, systemic flaw where groupthink absolutely thrives. Listen, if you're a young physicist today, your career, your funding, and your job security basically depend on you working on what everyone else is working on. Academia currently rewards conformity to the string theory paradigm while actively penalizing the independent risk takers.
Academia today heavily favors what Smolin calls the craftspeople. These are brilliant individuals, for sure. They excel at complex math, they follow established rules, and they solve known puzzles within the existing framework. But by doing that, the system is actively starving the seers, the true visionaries who ask deep philosophical questions, take huge risks, and invent completely new paradigms. Science desperately needs both, but right now, the seers are being pushed out. So, how do we fix this? Part 6, Saving Physics' Future. Smolin outlines a clear, actionable path forward for us. We've got to actively divert funding to support those seers and visionaries. We really need to encourage diverse, independent research paths instead of throwing all our eggs into the string theory basket. And we must completely reform academic hiring so that taking a massive intellectual risk is actually rewarded rather than severely punished. But above all else, physics has to return to its foundational roots. Theories absolutely must be falsifiable, period. We cannot accept beautiful, elegant math as the truth without rigorous, observable proof. If a theory cannot be tested in the real world, well, it's just not a finished scientific theory. The universe is full of mysteries just waiting to be solved. But I want to leave you with this one provocative thought. Progress requires courage. Are we, and the scientific establishment as a whole, brave enough to abandon the comfort and safety of beautiful, unprovable math and step back into the messy, observable, and ultimately true reality of our universe? Thanks so much for joining me on this explainer today, and keep questioning everything.